Hello everyone, welcome to NPTEL Digital Circuits course. This is the week 9th live session and I am Umashwari and today we shall solve some questions that may help you in your exams. So in this week, mainly we will talk about the semiconductor memories. So let us start. The first question is about static random access memory, which is also called as SRAM. So we have to tell each of the static SRAM memory cell contains. So does anyone know answer of this question? Okay, so let me answer. So SRAM is actually, if you remember your lectures, SRAM is the fastest memory in CPU. It is used as cache and it is volatile and it is made using CMOS inverters. So what it means is, so how many cells an SRAM would have? So an SRAM looks something like this. So we have two CMOS inverters. So this is an inverter. We also have another inverter. This is the second inverter. Let me make it the opposite way. Now these are just on both output and input are back to back connected. So these are four transistors just from the inverter. Then we have two access transistors. This is the bit line and word line. So here we have a word line. These two are bit lines. So in total, if we see, we have six transistors. 1, 2, 3, 4, 5, and 6. So this circuit is also known as 6T SRAM, where 6T means 6 transistors. So an SRAM cell has 6 MOS transistors. Okay, so let's see the next question. In a DRAM, periodic refreshing is not required. Information is stored in capacitor. Information is stored in latch. Both read and write operations can be performed simultaneously. Which option is correct? So DRAM, what is DRAM? DRAM is the stick memory that you use in your computers, like 4 GB RAM in your computers and laptops, 8 GB RAM. Like these, this is the RAM that we use, right? It actually is DRAM or dynamic RAM. So what is dynamic RAM looks like? It has one transistor and one capacitor. So it is also called 1T, 1C, one transistor, one capacitor RAM. So word line, this is bit line. So here what happens is the information is stored in form of the charge in capacitor. So our option, this is correct. Now why other options are not correct? So periodic refreshing is not required. So this is incorrect since it is a capacitor. Charge slowly leaks out of it through some leakage paths. So this needs to be periodically refreshed. If some high voltage, some high charge is stored here, we need to periodically refresh it to maintain the charge that it has. So it requires periodic refreshing. So this option is incorrect. Information is stored in a latch. It is not stored in a latch. It is stored in a capacitor. What do you mean by information stored in a latch? If you see the SRAM again, this configuration you can say is a latch where we have two back-to-back inverters. This is a latch. So in SRAM, information is stored in a latch, whereas in DRAM, information is stored in a capacitor. Both read and write operations can be performed simultaneously. This is not true because when you are basically trying to access this capacitor once at a time. So you cannot simultaneously both read and write. So the correct answer is in a DRAM, information stored in a capacitor. Next question. So this simple question you can directly answer. Just seen this. Right. Is one. Right. We just saw it is one transistor and one capacitor. 1T, 1C. Okay. Next question. In the following 3T configuration of DRAM memory cell, you need to first write a single binary digit 1 D in and then read it from the terminal Y. Assume the parasitic capacitor is discharged initially. For the operation, what will be the correct polarities of W, R, and Y terminals? So basically, this is our DRAM bit cell, and this is some modified form of circuitry that they have used for reading what is stored in the DRAM. So what they are saying is we have these three terminals W, this is V, this is R, and this is Y. So what do they want to know is first what you do is put D in equals to 1 in the write operation. Write a single binary digit 1. So you give D in 1 and to enable write, you put this write also 1. So what will happen is this since this at this gate 1 is there, so basically this 1 will whatever is at D in will transfer to V. So V will also change to 1. Basically, what does that mean? This capacitor will get charged. Initially, it was discharged, as mentioned here. Now, say when as soon as we enable this 1 and D in is 1, so this capacitor will get charged and we will have 1 here at this V. Now, we have done the first operation, that is the write operation. Now, what they are saying is read it from the terminal Y. So to enable read, we change this R to 1. Okay, so now let's see what is happening here, right? Now we have given 1 to the gate of this transistor. So what will happen? This 0 will transfer to here at this node. Let us call it node A. So A will change to 0. Now since you are reading, what you have again turned this transistor on. So this 0 will transfer from here to here at Y. So this Y will change to 0. So the question asks, what are the correct polarities of W, R, and Y? So W we have given as 1 for writing, R we have given 1 for reading, and Y we read as 0. Right? So just to reiterate, it is very simple. So whenever you have MOSFETs, whenever there is 1 at gate for NMOS, this is an NMOS. If there was a bubble here, it would have been a PMOS. But here it is NMOS. For whenever there is 1 at the gate of NMOS, gate terminal, what you will do? You just short these two, the other two terminals of the MOSFET. So whatever is here, if it is 1 here, it will be 1 here also. Similarly, when it is 1 at the gate here, so here it was 0 since it is grounded, so 0 will be here also. Same thing for this transistor. As soon as this transistor turned on, what happened? This 0 was here, this 0 transferred to output Y. So you just have to short these two. Is this clear to everyone? Okay. Next question is SRAM stores the binary information in dash. We have just seen this in one of the previous questions. Right. Internal latches is the correct answer. So if I draw the SRAM cell again, we have two back-to-back connected inverters, which is actually a latch, and then we have two access transistors. This is the SRAM cell. So information is stored here. Let's say somehow you put, let's say 0 here, it will be 1 here, 1 here, it will be 0 here. So at this node, it will always be 1, at this node, it will always be 0 until unless you bring some change. That's how data is stored in an SRAM cell. So answer is B, internal latches. So this is an internal latch made of two inverters. Okay, next question. Which of the following statements is false? First is SRAM memories has a shorter read and write cycles compared to DRAM. DRAM memories has a longer read and write cycles compared to SRAM. SRAM memories occupies minimal area compared to DRAM memories. SRAM memories occupy larger area compared to DRAM memories. Right. So option C is the false one. So if you see the statements again, SRAM memories has shorter read and write. So this is true. SRAM is actually fastest. And DRAM is slow. DRAM is slow because it has a transistor and a capacitor. And it is very time taking to charge and discharge this capacitor. So both A is correct, and so both A is true and B is also true. SRAM memory requires minimal area. This is false, as Payal has also stated. Since it has 6 transistors, it occupies maximum area. So this is also true. SRAM occupies larger area compared to DRAM. DRAM actually occupies the minimum area because there is just one transistor and one capacitor. So this is minimum area. Okay. Next one. Programmable array logic contains program fixed and array and fixed or array, fixed and array and programmable or array, programmable and array and fixed or array, programmable and array and programmable or array. Right. So in this question also C is correct. In PAL, it is programmable and a fixed or. In PLA, it is both programmable and programmable or. And one more thing is PROM, it is fixed and programmable or. So these are like the 3 types of programmable logic devices. Mainly these are used to uh, make combination circuits. We will see some of their examples in coming questions. But just to remember, PLA has programmable and fixed or. PLA has programmable and programmable or. PROM has fixed and programmable or. Which of the following memory technologies is volatile in nature? Right. So first is, what does volatile mean? Volatile means that, let's say, in any of these memories, you turn off the power. Let's say you're supplying some voltage, right? VDD and ground. Let's say you turn off this power, or you turn off, your shut down your computer. Will that information be still stored in the memory when you restart it or not? That is called as volatility or non-volatility. So volatility is on, in a simple term, on restart or on power off, data is erased. When this happens, it is called as volatile. The other term will be, if it is non-erased, that means it is non-volatile. So here SRAM is the volatile memory. When there is no power, the data in SRAM is generally erased. Okay. Which of the following memory technologies is not programmable? Okay, so this is also straightforward. So if you see what does EEPROM means? It is electrically erasable programmable. Electrically programmable. So this one is programmable, right? This is not our answer. EEPROM here also P stands for programmable. SRAM we have seen in SRAM you can read and write with the help of this word lines and bit line. You can store either 0 or 1 at any of the nodes. And what is fuse? Fuse means, so this is also programmable. Fuse means like you have permanently joined two connections. Let's say there is some connection, some A, B, or C is coming. So you have like permanently joined these connections. That is like fuse. So once it is permanently joined, you cannot change it. So it is not reprogrammable. Yeah, pilot should be reprogrammable. I think. So so the answer is fuse. Okay. Next question. What is the ROM size when it has 16-bit address lines as input and 8-bit data lines as output? Okay, so let us see. So what does this means? We have, let's say this is some memory bank. So they are saying we have 8-bit data lines as output. So it's like we have 8 outputs here. So that means we have like total 8 bits. 2, 3, 4, 5, 6, 7, 8. Right? So these are like 8 bits. So each word contains 8 bits. Okay. Now we have 16 address lines. What are they saying? Like you have some address lines, let's say A0 to A16, which actually access these rows. Now to access each row, uh, or you can say what do we have is we have a decoder here. So this decoder, if you give any 16-bit address here, this decoder will point to some particular row in this memory bank. Then you can like read or write whatever you want in these particular 8 bits. So for 16-bit decoder, you can have how many rows you can access? You can access 2 to the power 16 rows. So that just means you will have here 2 to the power 16 rows in this memory, and you have 8 columns, which is given by as you have stored 8-bit data in each row. So memory size is 2 to the power 16 cross 8 bits. Yes, sorry, A0 to A15. Okay, so can someone tell me like what would be this memory size in KB, kilobytes? Dinesh is 65 KB. Do you have any other answers?
512, sir.
512. Okay. Files is 524. Okay, so let us see. So basically what we have is 2 to the power 16 cross 8 bits. So what I want is answer in kilobytes. So one thing you know is 1 byte is equals to 8 bits. So now what we can do is we can write it as 2 to the power 16 bytes. We change it 8 bits into 1 byte. Right now, what we can do is we can break this 2 to the power 16 into two parts. It is 2 to the power 6 into 2 to the power 10 bytes. Now, what is 2 to the power 10? This is kilo, right? 1k equals to 2 to the power 10. So you have 2 to the power 6 kilobytes, and 2 to the power 6 is 64. So your answer is 64 KB. 65 is also correct. Actually, it is not wrong, but yeah. Okay, so let us see the next one. A memory unit of 1024 cross 64 is specified by the number of words times the number of bits per word. How many address lines are needed for the memory unit? So basically what they're saying is you have some memory bank 1024 cross 64, and 1024 are your number of rows and 64 is your number of columns. You have 64-bit data stored. number of bits per word. So basically each row in a cell we call it a word. So we have to tell how many address lines are needed to access these 1024 rows. Okay, so you have correctly answered. It is 10, right? Because 2 to the power 10 is 1024. So you need 10 input decoder here, which will access these 1024 rows. And these 10 inputs are the 10 address lines. Okay, so this one was easy. I hope it is clear to all. Next, sorry, yeah. Next question is, which of the following statements is true? First is A, Hamming code can correct and detect only single bit errors. B, Hamming code can correct and detect up to 2-bit errors. C, Hamming code can correct and detect up to 3-bit errors. D, Hamming code can correct and detect up to 4-bit errors. Okay, so most of you have answered A, which is correct because at max Hamming code can detect 2-bit errors, but it can never correct. So option A is correct. It can correct and detect only single bit errors. Next question. What is the size of Hamming code for a 10-bit data word? Please solve this. I'll be back in just a minute. Okay, so let us see this question. So most of you have answered A. So let's see. So let's say if your size of data is n, which is 10 given here, size of code is, the number of code bits is, let's say, k. So total size is n plus k. So which is what is being asked in the question. What is n plus k, right? And the condition for this is, sorry, so the condition is that the Hamming code must satisfy is 2 to the power k minus 1 would be greater than or equal to n plus k. So 2 to the power k minus 1 should be greater than or equal to 10 plus k, or 2 to the power k minus 1 minus k should be greater than or equal to 10. Now we can, so we have this equation 2 to the power k minus 1 minus k equal to 10. Now we can put maybe some values here. If let's say k equal to 1, k equal to 2, k equal to 3, k equal to 4, k equal to 5, it's what we can have, right? For k equal to 1, what is this? 2 to the power 1 is 2 minus 1 minus 1, which is actually 0. No, so it is when 2 to the power 2 is there, 4 minus 1 minus 2, which is 1. 1 is still not greater than or equal to 10. It is 3, 8 minus 1 minus 3, which is 4, still not greater than or equal to 10. Then k equals to 4 is 16 minus 1 minus 4, which is 11. This is greater than or equal to 10. So k equals to 4 is your answer, right? So number of k should be equal to 4. So a total Hamming code n plus k equals to 10 plus 4 equals to 14. So you should have 14 bits. Option B is correct. Is this clear to all? Those who have answered A. Please let me know if there is any doubt. Okay, so I'm assuming it is clear to all. So let us move on to the next one. A 12-bit Hamming code read from a memory location. The Hamming code contains 8-bit data and 4-bit code word. What was the original 8-bit data word stored in the memory location if 12-bit Hamming code is this? So you have this 12-bit Hamming code, you have to tell what is the original data. So please spend a few minutes to solve this, then we will do it together. Okay, is anyone close to an answer? Okay, Payal has given an answer. Dina has also given an answer. B. Okay, so let's do one thing. This question is a bit complex. Let us first solve this one. This is a bit easier. I think most of you will be able to answer this one. So can you try this one first? Then we'll come to the previous one. So this question is find the 12-bit Hamming code for the given 8-bit data. So you have an 8-bit data given, you have to find the 12-bit Hamming code. Now this is almost opposite of what was asked in previous question. But please try this one, then we'll solve the previous question. Okay, is anyone able to solve this one? Dina says B. Pile also says B. Okay, B is correct. So let us see this question. So basically, you have to find the 12-bit code, right? So it should have 12 bits, right? And out of these 12 bits, we will have 8-bit data, which is given here, and we will have 4-bit for parity. These 4 bits come at 2 to the power 2 to the powered position. So you will have, let's say, P1 here, P2 here, P4, and P8. So if you remember the videos, you would know this. And here you will directly write the remaining bits in the data. So it is 1 1 0 0 0 0 1, 1, right? And now to calculate what these parity bits would be, so what would be P1? P1 equals to XOR of. So how do you determine what is P1? So what are the numbers in this P1? So let me just write those numbers first, then we will see 3, 5, 7, 9, 10. So the numbers which are the digits that are covering at third position, fifth position, seventh position, ninth position, and 10th position. We take XOR of these. Similarly, for P2, it is XOR of 3, 6, 7, 10, 11. P3 is XOR of 5, 6, 7, and 12. And P4 is XOR of 9, 10, 11, and 12. Now, how do these numbers come from? It is like, let's say you have a 4-digit number, say 0000 or 0001. So P1 determines, takes care of this, P2, P3, P4. This is 100100011 or 100. So I write until 7. 1, 2, 3, 4, 5, 6, 7. Then will be 8, right? Okay, so all the numbers which have 1 in there in this in their first bit, those are 1, 3, 5, and 7. So 1 is itself is the parity bit. So 3, 5, 7, they will come here, and after that it will be 10019, and 10 is 1010. It should be 11, sorry. This is 10. Let me add a page. Yeah, it should be 11. 10, 10 is 10, and 1011 is 11. So all those so all those numbers in whose binary expansion has 1 in their LSB, they all will come here in XOR of P1. Similarly, all those in the second bit we have the ones. Those are, so what are these? In 2, so 2 itself is the P2, so we will not consider 2. So we have in 3, we have in 6, 7, 10, 11. It will, so in all these 3, 6, 7, 10, 11, in these, in their binary expansion, we have ones in the second bit. Similarly, in the third bit, wherever 1 comes in here, it is 4. 4 itself is the parity bit. It should have been P4, sorry. P4 and P8. So it is 5, 6, 7, and 12 will also have it. 12 is 1100. It is 12. So in 5, 6, 7, and 12, you have 1 in the third bit. And in 8, in the last bit, wherever there is 1, it will come. So it is 8. 8 itself is the parity bit. 9, 10, 11, and 12. So in all these 4, there is 1 in the last bit. in the fourth position. So these four will be XORed for P8. I'll ask, sir, why do we not take position 2 for P2? This, so P2 itself is taking this place, right? That's why. Out of these 12, second one is already occupied by P2. Similarly in P4, right? We have not taken 4, but 4 also has 1 in the third bit. Similarly in P8, 8 also has a 1 in here in the fourth bit, but that place itself is occupied by P8. Okay, so now we know where do these numbers come from. Now what we have to do is XOR. So let's see what digits are there. At third position it is 1, at 5 it is 1, at 7 it is 0, at 9 it is 0, at 11 it is 1. So in XOR, when you have even 1, your output is 0, odd 1, output is 1. So here it is odd 1, so this will be 1, P1 will be 1. For P2 it is 3, 3 is again 1, 6 is 0, 7 is 0, 10 is 0, 11 is 1. So 2 ones, that is even, so P2 will be 0. For P3 it is 5, 5 is 1, 6, 6 is 0, 7 is 0, 12 is 1. Again 2 ones, so it will be 0 even. Let me write it just for clarity. Now for P8 we have 9, 9 is 0, 10 is 0, 11 is 1, 12 is 1. So again, student P4, I always make this mistake. P8 is 0, again even ones. Okay, so in your number now you know this is 1, this is 0, this is, let me write with some other color. Okay, this is 1, this is 0, this is 0, and this is 0. Rest all the numbers we can write as is. So this is your final code, 12-bit code. And this is option B. So is this clear to everyone, whatever we have done? Okay, so now in case if you forget these numbers in your exam, so best case would be you just remember these so you do not waste your time. But in case you forget, you know from where these numbers are coming. You can write them on your own. If you forget which numbers I have to take XOR. So how to fill the parity bits, we know this. Now let us come back to the previous question. Now this question says, yeah, they have given a 12-bit code. We have to find the original 8-bit data word. So some of you have answered option B. So let us see. We have 12 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0. Now we know there will be P1 here, P2 here, P4 here, and P8 here. So those who have answered, like whatever is remaining should be your answer, right? I think that logic you have used, which is 111, sorry, 1101, 1110, 1101, 1110. So by that logic, B is correct. But one thing we are missing here, right? We have been given a 12-bit Hamming code. It may be possible, like there is some error in this. So we have to check it for error. And if there is any error, we have to correct it. That is the whole purpose of these parity bits, right? Like if there is some error, we can correct it. So maybe this answer is incorrect. Maybe that we have to check. Or like there is some error in this 12-bit code and that we have to correct using these four parity bits. So, so we have to check first what is the error bit. So can anyone, so maybe you can try it out again for 1 minute by keeping in mind that you have to check for error. So let me know if you get any of the answer. So Dr. Nazia says syndrome is 1000. So syndrome is actually, okay, ninth bit in error. Okay. Is anyone else getting the same answer? Okay, so let us check this. So let me maybe copy this here first. Just erase this. So this we understood what was these were the parity bits. How do we calculate these parity bits? Now we want to check if if there is parity or not. So instead of P, we introduce C, C1, C2, C4, and C8. Now what is different in calculation of C in this C's instead of P's? So this calculation is for P1. And to do for calculation for C1, what we will do? We will include the first bit also here. We'll include, so let me write it with another color. We'll include 1 here. Similarly in 2, he will include 2 here. In 4, we will include 4 here. In 8, we will include 8 here. So this is how we determine the check bits. Okay. So now, now let us see if all the bits are correct or not. So in the first bit, we have 0, third is 1, fifth is 1, seventh is 1, ninth is 1, and 11th is 1. So we have 5 ones. So C1 is 1. C2, okay. So first let me tell you C8, C4, C2, C1. If it comes to be 0, 0, 0, 0, then only there is no error. In case there is any other thing, that means that this sequence tells us the position where there is error, which is actually the sequence that Dr. Nazia was talking about, the syndrome. So let us find out. So C1 we have found out to be 1. C2, let's see, it is 2, 2 is 0, 3 is 1, 6 is 0, 7 is 1, 8 is 1, and 11 is 1. We have 4 ones, so that means C2 is 0, even ones, it is odd 1, and C3, 4 is 1, 5 is 1, 6 is 0, 7 is 1, and 12 is 0. We have 3 ones here. So C3 is 1. Sorry, I should not write C3, it is C4, odd ones. C8, 8 is 1, 9 is 1, 10 is 1, 11 is 1, 12 is 0. C8 is 0, even ones. So your C8, C8, C4, C2, C1 is 0, 1, 0, 1. This is actually 5. So that means your error is in fifth bit. So what does that mean? This here this 1 should be 0. Rest all the bits I'll write as is 0, 0, 1, 1, 0. I'll only write the non-parity bits. So your finally that this is your data, right? Error was there in the fifth bit. So your answer is option A. So Dr. Nazia and Dina, I think you were making some mistake in the calculation. So please check if it is clear. I hope this is clear to all. If not, please Let me know.
Yes, sir. I did not add 1, 2, 4, and 8 actually.
Okay. So yeah, so that is the only difference while checking for errors. For when calculating parity, we do not include these. But while checking for parity, sorry, while calculating parity, we do not include it. But while checking the code for error, we include these 1, 2, 4, and 8. This is the thing to remember in this question. Rest everything is, I think, straightforward. Okay, so this is clear. Let us move ahead. Okay, so these are all the questions for parity. Now I have some questions on. So what is this circuit? This is PLA, where we have programmable and programmable or. What does this mean? How are we saying programmable? Like there are no fixed connections to all these. Like it could have been this, or this, or this. So this this variability in choosing these connections is the programmability. So these are the AND gates. So this is programmable AND. Similarly in OR, we have programmability. So this is PLA, programmable AND and programmable OR. Okay, so this is one thing. Keep it somewhere in the corner. Okay, now the question asks what are the outputs of the following circuit. We have to tell what are the outputs F1 and F2. So please spend a minute, then we will solve this. File says A. Okay, Harsha also says A. Okay, so let us see this. So let us see what are the outputs of these AND gates 1, 2, 3, and 4. So here we have these connections. This is B bar. This is A. This is A. This is A bar. Let me just write all these connections. C, C, B, C bar, and B. Okay, so the AND gate outputs are A B bar, A C, C B, and A bar, B, C bar. Okay, so these are the AND gate outputs. Now for OR gates, let me call it, let's say O1 and O2. So O1 would be OR of these two, right? So O1 is AC plus BC. You write it as BC, and O2 will be OR of these three because these three are connected. O2 is AB bar plus AC plus A bar B C bar. Now we have two XOR gates. So F1 is O2 XOR with sys 1, and F2 is O1 XOR with 0. F2 is O1 XOR with 0. So one thing to remember it for XOR gate, let's say it is X XOR 0, X XOR 1. So always X XOR 0 is always X, and X XOR 1 is always X bar. Why? Let's say in the first case, X can be either 0 or 1. So 0 XOR 0 is 0, 0 XOR 1 is 1. So that means X XOR 0 is X. In this case, 0 or 1, 0 XOR 1 is 1, 1 XOR 1 is 0. So if this was X, this output is X bar. So these two you need to remember. X XOR 0 is X, X XOR 1 is X bar. So O2 XOR 1 will be O2 bar, and O1 XOR 0 will be O1. So your F1 should be AB bar plus AC plus A bar B C bar whole bar, and F2 would be AC plus BC. So AB bar plus AC plus A bar B C bar whole bar. This is option A. Is this clear to everyone? Okay. Next question. Okay, so let us see this. This one is simple. Sorry. Here it is. XY. This is XZ bar. This is XY bar, and this is YZ. A is simply XY plus XZ bar. B is XZ bar plus XY bar plus YZ. So it is option B. This was straightforward. Okay, next one. So the connections are not clear. Let me make them. Okay. So you have to tell the answer now in terms of min terms. So this is the circuit. Please try to solve it. Okay, so let's solve this. This is C bar, A bar. This is A, B, C bar, B bar, AC. This here is AC, B bar, C bar, ABC, and A bar, C bar. So 2 here is ABC plus AC, and 1 output is A bar, C bar plus ABC plus B bar, C bar. F2 is A bar, C bar plus ABC plus B bar, C bar XOR with 0. So F2 is simply the same thing, A bar, C bar plus ABC plus B bar, C bar, and F1 is AC plus ABC XOR with 1, which is AC plus ABC whole bar. Or if you see, it will you take common, maybe what you can do is AC bar. B plus B bar will be B plus 1 will be 1. Okay. Now I have to tell in terms of min terms. So what you can do, maybe if you're not able to solve it directly, you can make a 3 variable K map and then try to solve it. A bar plus C bar. Okay. So F1 is A bar plus C bar. So A bar is this and C bar is this. So it is 0, 1, 2, 3, 4, 6. F1 equals to sigma n 0, 1, 2, 3, 4, and 6. And for F2, you can draw another K map here. We have A bar, C bar. So this is A bar, C bar, and we have ABC. This is ABC. We have B bar, C bar, B bar, C bar. So we have F2 equals to sigma n 0, 2, 4, and 7. So this is option A. Is this clear to everyone? Since nobody answered this one. Okay. So we did the same thing, except the answer was asked is this time in terms of min terms. So you should expect these kind of questions in your exams where multiple concepts would be uh, merged. Okay. So next question. This is the last question for today. So please solve this, then we will finish for today. I hope you will be able to solve this. We have solved many such questions now. You have three outputs now, F1, F2, and F3. Okay, so we have two answers at B. B is correct. So let us solve this. C bar, choose similar color. C bar, this is B bar, this is B, this is B bar, C bar B, C B, A. This is A bar. Okay, so here we have, let's say, B bar, C bar. B bar is actually 0, so nothing will add. A bar, B, C bar. This is ABC. Now these OR gates. F1 is B bar, C bar plus 0 plus ABC. F2 is again 0 plus ABC. F3 is B bar, C bar plus A bar, B, C bar. So answer ABC, B bar, C bar, ABC and A bar, B, C bar and B bar, C bar. Okay. So option B is the correct answer. So I hope this was clear to everyone. So if there are no more questions from my side, so if everything is clear, we can close the session for today. Okay. Thank you, everyone. See you next week.